Implementing LeNet and design on one CNN model. Introduction to Artificial Intelligence. Artificial intelligence has revolutionized numerous fields, from healthcare to finance, by enabling machines to learn from data and make decisions. A significant aspect of AI is machine learning, which includes deep learning techniques that utilize neural networks to analyze vast amounts of data. Among these techniques, convolutional neural networks have gained prominence, especially in image recognition tasks. This article will focus on implementing LeNet and design on one CNN model, providing learners with a solid foundation to build their own CNN architectures. What is LeNet? LeNet is one of the pioneering architectures in the field of CNNs, developed by Yann LeCun in the late 1980s. It was primarily designed for handwritten digit recognition and has laid the groundwork for many modern CNN architectures. LeNet consists of several layers, including convolutional layers, pooling layers, and fully connected layers, all of which work together to extract features from input images. Key components of LeNet. Convolutional layers. These layers apply convolution operations to the input images, allowing the model to learn spatial hierarchies of features. Pooling layers. Pooling layers reduce the spatial size of the representation, which decreases the number of parameters and computations in the network. Fully connected layers. These layers connect every neuron in one layer to every neuron in the next layer, enabling the model to make predictions based on the features extracted by previous layers. Implementing LeNet in your CNN model. Step-by-step guide to implementing LeNet. To implement LeNet in your CNN model, you can follow these steps. We will use Python with the TensorFlow and Keras libraries for this example. 1. Start by importing required libraries. 2. Then define the LeNet architecture as shown below. 3. Then compile the model. 4. Once the model has been compiled, the next step involves training the model. 5. Finally, the final step involves the evaluation of the model. Example use case: handwritten digit recognition. To illustrate the effectiveness of implementing LeNet, consider the NIST dataset, which contains images of handwritten digits. By applying the steps outlined above, you can train your LeNet model on this dataset and achieve impressive accuracy rates. 1. Load the NIST dataset. 2. Train and evaluate your model. By following the training and evaluation steps, you should be able to achieve a high accuracy on the NIST dataset, demonstrating the power of implementing LeNet in your CNN model. Designing your CNN model. While LeNet serves as a great starting point, designing your CNN model involves customizing the architecture to fit specific tasks. Here are some considerations for designing an effective CNN. Layer configuration. Experiment with the number of layers, types of layers, and their configurations to find the best fit for your dataset. Activation functions. While LeNet uses the TAN activation function, modern architectures often utilize ReLU or its variants for better performance. Regularization techniques. To prevent overfitting, consider implementing dropout layers or L2 regularization. Data augmentation. Enhance your dataset by applying transformations such as rotation, scaling, and flipping. In conclusion, implementing LeNet and designing your CNN model can significantly enhance your understanding of deep learning and image recognition. By following the steps outlined in this article, learners can create a foundational model that can be further refined and adapted for various applications. As you progress in your AI journey, remember that experimentation and continuous learning are key to mastering these technologies. For further reading and scholarly sources on CNNs and LeNet, consider exploring the following. LeNet 5. Convolutional Neural Networks. Deep Learning by Ian Goodfellow, Yoshua Benjo, and Aaron Corville. A survey on deep learning in medical image analysis.